Alrighty, let's go on to part 2, functions. Okay, what is a function? A function is a relation, okay, which we learned about in the last lesson, in which each domain element has exactly one corresponding range element. What does that mean? You can also state it as a function is a relation in which each first coordinate appears only once. Okay, we know what the first coordinate is. The first coordinate is only the x values. A function is a relation in which no two ordered pairs have the same first coordinate. Well, let's just make this simple. Okay, let's have a set of coordinates. We're going to call it S. And those sets of coordinates are going to be 2, 3, 1, 6, 2, root 5, and 0, negative 1. Okay, we know our first coordinates here. Here's our x, 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 x. We know our second coordinate. I'll put it right here. It's y, 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 y. Those are our second coordinates. So if we draw this out, here's going to be all our, first coordinates. Here's going to be all our second coordinates. I apologize for the horrible drawing. So we put all our first coordinates in here. We have 2, 1, and 0. Notice we have a 2, 1. There's another 2 there. We don't have to repeat. And 0. Then we have 3, root 5, 6, and negative 1. These are all our second coordinates here. So x and y. Now, as you can see from what it states right here, it says a function is a relation in which the first coordinate appears only once. Well, obviously you can already tell the 2, so this is going to be already not a function, but I'm going to show you why. A function is a relation in which no two ordered pairs have the same first coordinate. Well, we already see that. And here's what's happening. If you see it kind of pictorially, the 2 can go to the 3. Okay? But the 2 also goes to the root 5. And then 1 goes to the 6, 0 goes to the negative 1. So without doing the picture on another one, we can have, say, another set of coordinate pairs, call it T, and we're going to say 1, write this better, I apologize, 1, 5, 3, 5, root 2, 5, and then negative 1, 5. A horrible 5 at that. Okay, well, let's look. Do we have a relation in which the first coordinate appears only once? Well, let's look through here. I've got a 1, a 3, a root 2, and a negative 1. Okay, perfect. So I do not have any repeating x's. Function is a relation in which no two ordered pairs have the same first coordinate. We've already figured that out. Now, do notice I do have the same second coordinate, but that doesn't mean anything. There is no rule that says that can't happen. We are only concerned with the x's. I cannot have the same x coordinate. That's what we're looking for. If that happens, okay, like here, this one, not a function. Here, this is a function. And we're going to see this more. Like I said, we'll get into Hawks. You're going to see some more examples graphically, what this means. So scrolling down, if any vertical line intersects the graph of a relation at more than one point, then the relation is not a function. Well, that sounds great mathematically. What does that mean in the real world? Okay, let's take a graph. Okay, we're going to have two separate graphs here, but the first one, let's have a line that looks like this. Okay, on that line we can have 2 points. here, and here. And we'll say this one is negative 2, 2, and then this one here is 2, 2. The vertical line test says this. I should be able to draw a vertical line going up and down, basically parallel to the y-axis, okay? And it should only hit a point one time. Notice here, it hits a point here, it hits a point here. If I want to come over here and draw a line, it only hits a point here. It only hits once. The line only intersects, that's a little bit, I'm going to go a little bit thicker. The line only intersects one point only. Okay, so graphically, this would be a function. Notice it's kind of from our last example, our last definition. I will have a different x coordinate everywhere on this line, but I have the same y. That is fine. So that kind of shows our second example from the top. Well, what would something look like that's not a function? Let's just draw something here, and let's just put a point here, and let's put a point here, but let's draw something that looks like this. Okay, would this pass the vertical line test? Well, here it does, and here it does. But the biggest problem is right here. Here, it doesn't. Okay, and if we wanted to just some arbitrary points, let's just pretend like I knew exactly where these were. Let's just say this one was at negative 1, 1. This one right here would be at negative 1, 0. And then this one right here could be at negative 1, negative 1. Well, notice we have x values that are all the same. So graphically, you can see why this would not be considered a function. Okay, moving on. The graph of the linear function y equals 2x minus 3 is shown here. Notice this would be a function. Okay, what would its domain be? Well, if you're your little guy and he's walking along and he looks down and he looks up, that line is eventually going to be where he can see it. So the domain would equal negative infinity to positive infinity. You can also just say all real numbers. Well, how about his range? Okay, well, as he goes up and he's looking left and he's looking right, notice that no matter what happens, he's always going to see that line. So the range would also be negative infinity to positive infinity, or all real numbers. So what does this tell us? A linear function, which is what this is, or a linear equation, okay? And this one right here, the linear equation is y equals 2x minus 3. Notice that this is our slope, okay? This is our y-intercept. Just kind of a little bit of a review, okay? They are always going to be this. Okay, they will always have a range and a domain of infinity. Well, okay, I say that, not always. They're always one of them is going to have that. Okay, so just kind of be very wary of that. Let's go down here. So we see our equation. Well, this right here is the equation. This is what you just saw. To change it to function notation, we're just going to be switching the y with that. Okay? Why is that? Because we're changing the relation a little bit. We're kind of making what I would like to call a function machine. Okay? I'm going to pump an x in here. I've got an x. Here's my little machine. Okay? It's got like a little hole here. I throw an x value in here. This thing starts to do its thing, and it's going to pump me out, Okay, have a little conveyor belt here. It's going to pump me out a y value. So when I put in a function x, if I put in a coordinate point x, like say 2, okay, it's going to give me my y value. That's all this is trying to say. How you would read this is you read f of x, okay, which just means function of x. This will become a really big mainstay as you kind of go forward in math. So let's just do a couple of examples. Like I said, we're going to get into more of these whenever we start doing the hawk, so don't fret. So for the function g of x, they don't always have to be f, okay? It can be g of x. You'll see h of x. You'll see h of t. Sometimes you'll see different things. It depends on what your point has. Notice how we're changing the relation now. Not everything always has to be xy anymore. Okay, so for the function g of x, for x plus 5, find g of 2. All we're going to do is we're going to take this 2. So we're going to rewrite this as g of 2. Everywhere that there's an x, we're going to replace it with 2. Plus 5. And when you do that, you're going to get 13. Okay, for the function h of x, notice once again we changed it. Change it to h of 4. You can put it into quadratic equations. So I would have h of 4 equals 4 to the power of 2 minus 3 multiplied by 4 plus 2. Whenever you do all this, you end up getting 6. So, and we'll continue on with some Hawks lessons, and you'll be able to see a lot more of this. You're going to see some different domain variations, especially some linear and some in fraction form, finding the domain and range of something of a fraction form. So, all right, on to Hawks.